It's like, all right, so let's talk about feature engineering and model tuning. All right, so let's frame this up a little bit. Actually, hopefully they'll do it. Yes. Okay. So we defined our business problem and our problem formulation. That was pretty much day one, right? And then we got introduced to SageMaker right at day one. And then day two, we did some problem formulation and some collection integration and pre-processing. We touched that to a certain degree. And then yesterday, which was day three, this is where, you know, we finished out kind of data processing, and we talked about model training and model tuning, and then we had access to basically run the model. And we talked a little bit about model evaluation because we needed to do those two in order for us to be able to get to the lab. And then, you might have heard me joking yesterday. I was like, wow, the accuracy of my project's really bad. And I was like, yeah, I probably wouldn't share that with a customer either. Right? I don't know if you saw that in chat. Right. And so this is where, you're at that phase where you're like, wow, this didn't really yield the numbers that I wanted to. It's not good enough for our business problem. What do we need to do now? Right. And so part of it is, obviously engineering or doing some kind of data augmentation or something to improve our predictive quality, right? And whether we're using, accuracy, or we're wanting to avoid false positives and false negatives, right? For example, with like recall and precision, or whether we're using a mixed score, like the F1 score, or if we're not doing classification, maybe we're doing regression, we're just wanting to improve, MSE and RMSE. Like, we're just trying to make that better, right? Like, and we're just trying to make it more applicable to our business problem. This is the common phase. Like, you've gone through the thing, and then you're like trying to figure out how to make it better, right? This is where also data science really becomes something where, like, people joke about it as if it's an art, but it's really just being curious and methodical. And it's like, it's funny. There's like three things that really matter here. It's like, you got to be curious because you got to explore beyond what you think your biases are. You got to be methodical. And then the other thing is that it's really helpful is like contextual. Like, what are the things that you don't know? You got to really know how the model works. You got to know how the math works. You got to know what the metrics mean. And you have to, in a sense, be able to know exactly how your inputs are being translated out to your outputs. Now, obviously, as you do that, you get deeper and deeper into the math. And it's really good to work with a team on this kind of thing, because I tell you, one individual will always get hooked up on something. Like, I won't see something that's very obvious to someone in about 5 seconds. So just as a general rule of thumb, curiosity, context, and being methodical are probably keys. I said that to somebody once, and they said, like, that sounds like good things to just have, whether you're a developer or an architect or a sysops person or a machine learning person. It's like, yeah, sure, that sounds right, right? Curiosity, because the minute you're like, like the other day, someone was like, it sounds like containers are just virtual machines kind of redefined. It's like, I mean, you could put it in that context, but then you just think it's the same thing you've seen before. You're not actually open to exploration. And I got to tell you, when you're trying to solve a problem, being open to exploration, like when you're trying to improve a model, right? Being open to exploration is just incredibly key. And then, so, and the methodical piece, and the reason that the methodical piece is also relatively important is that there are like, 300 dials, not including all the data points, that you could turn to kind of like make this work. Now, unless you have a system like the hyperparameter auto tuning that we're going to talk about to kind of like test everything in order to derive a better score, if you're doing it yourself, you're turning the dials yourself. Like, you're thinking, well, maybe I should drop this column, or maybe I should run PCA and pick the highest correlated value, and drop the others. It's like, you want to like capture everything that you've done, all the assumptions you made, and it's kind of a exhausting process, because in this day and age, we're just like, let's go, and you're going to do this all under time pressure. So, being methodical, even though it might slow you down a fraction of a second, and capturing what you're trying to accomplish and what you're doing and the assumptions that you're making and the changes that you've made are really going to help. People get really ticked off because they're like, I don't want to take notes. I don't want to track everything I do, right? You have to in some form or fashion, whether it's a repo, a notebook, or something. Wait, that's me on my soapbox. Let's move on. All right. So we're going to talk about feature engineering. We're going to talk about hyperparameter tuning. Oh, can I also say one other thing? People's attitudes about this is also extremely important, right? If people aren't buying into the kind of the joy of like solving these problems, or they see the challenges as like, man, this is a horrible disaster. I just want to point out that like businesses, people are people, businesses are going to be businesses. Like, know what you know. If the business is always going to come to you with requests, for example, that are just ridiculous, out of scope, either accept that or just move on, right? Because like, I think sometimes we rail at things that we want to change, but like changing people is really hard. Changing data is a lot easier. So just something to throw out there. I know a lot of data scientists and engineers and ML specialists who have really great careers because they accept people as they come to them. They accept how businesses operate and they do their work and they love it, right? I have others who like get distracted by all the politics and the fights and, oh, I wish they would do this differently. And anyway, that's a whole other thing, but yeah, just something to keep in mind. All right, so with feature engineering, which is probably a little bit easier than people engineering, right? So for example, this is again, and I think in your notes, it even says it's like the science and the art is that, yeah, actually it does say science and art. So just know that like, what you're trying to do, feature engineering is where you're trying to extract more contextual meaning information from the existing data for the sole purpose of just making your prediction better. And frankly, to kind of make it learn faster, right? Because time is the one resource you can't get back. Now, you're not necessarily adding any new data, but you're taking the data you have and maybe making it more useful. And when I say you're not adding new data, you're not adding new like actual data, right? So it might rely on domain knowledge, by the way, to make it more effective. As an example, you might say, well, how come these dates have much higher sales rates than others? What could be causing this? And here you have engineered a feature of the data by adding, in a sense, a meaningful dimension that wasn't part of the original data set. But like you added Saturday, Sunday, Monday, Tuesday, and guess what you found out? People buy more on the weekends. You know why? I don't know why. We can speculate though about it, right? Is it because people have more time? Is it because they're not working? Is it because they feel more relaxed? Is it because that's when they run their errands, right? Is that because that's when they have fun? Like, what is the nature of the purchase? I don't know. Those are all just made up, right? So then you can just do some analysis and just impute that as an additional impute that. You can just add that to your data set, right? What's funny about that is that that gives your like existing data more meaning and therefore you can train better. So feature engineering is made up of a couple of different like steps that we kind of go through, which is one, feature extraction, right? And feature selection, which really can reduce the size of your data set, which can really help with overfitting, right? Won't really help with underfitting. Although, you know, it can make the data you have more meaningful, right? And then feature creation and transformation. So the first two basically deal with reducing dimensionality. Like how can we extract, how can we condense, right? How can we select obviously the ones, the data features that are probably the most significant for us in our data set. Now, dimensionality refers to the number of features that you have in your data set, right? The number of like qualities and qualifiers, characteristics, right? And the phrase, the curse of dimensionality, right, refers to the fact that models are going to have a difficult time finding patterns you want them to identify when the data goes in like 50 different directions. There's too many features to sort through when you're trying to correlate patterns with too many different dimensions, some of which may not be relevant, right? If you're doing sales forecasting, right, you might have data in there. Like what was it that Jonathan said? The eye color, right? Eye color. You might have eye color in there. Like who cares? That doesn't matter. You might have someone's birthday, employee birthday. It's like, and you know, obviously, if you're trying to forecast like date of sale, seasonality, or did you run sales, like stuff like that would be like super relevant. Data outside of that certain set may not be relevant. Now, be careful with that, because there's data in some cases that you think is not relevant. It might be interesting to run models with certain data sets in there when you're not under a time crunch to like produce the actual thing. So just know, like, experimentation can also be fun in this space, right? But let's talk about feature extraction and feature selection, right? Versus feature creation. Let's look at both of these in turn, right? So for example, in this case, it's like you could automatically reduce the dimensionality of your data by creating new features from existing features, right? So that, like, you could extract, for example, looking at a car, that means a tire is going to be present, headlights, windshield, right? In this case, by the way, you could also use this to identify that this is a vehicle. Now, I wouldn't necessarily identify this as a car. Probably, does it have 4 tires? It's probably likely a car, not 2 motorcycles side by side, right? Which, by the way, you run into that kind of a lot if it's doing that kind of recognition. So like you can extract other features from like your data set. So like in this example, like with image recognition, right? One of the ways that we would do is we extract features from individual data set individual images. So if the image is a car, you can extract some useful aspects of this, like windshield, headlight, tires, windows, grill, that kind of thing. So instead of having raw pixels make up your data set, you have features or columns, right? Columns such as the windshield is present, or tire is present, or headlight is present. These features make it easier for a machine learning algorithm to learn from the image data and eventually start to recognize things like that are more complex, like faces and animals and landscapes and stuff like that. So that's one feature extraction strategy, is instead of trying to do the whole thing, you could actually pull chunks out that are common elements when you're trying to identify, for example, the type of vehicle, or even that it is a vehicle, right? You might instead just look at, does it have a windshield? Does it have a headlight? Does it have 4 tires? Can we even tell it's got 4 tires? Does it have a tire? Well, it's probably a vehicle, right? And then from there, you can do other isolations and extractions. Other strategies, for example, is you could use natural language processing. By the way, one of my friends is like a coach, and every time I say the words NLP, he thinks I'm talking about neuro linguistic programming. Do you know what that is? Anyway, I didn't. So he thinks I'm talking about neuro linguistic programming, which is apparently some kind of like quasi hypnotic kind of like biochemistry kind of manipulation. It's not bad. It's just something you use to train the nervous system. I thought, that's an interesting. Anyway, natural language processing will basically allow you to isolate to like different like key aspects, like topics and whatnot, or good, like paraphrasing, like being able to isolate kind of like significant and key concepts and words inside of a corpus. Structured data, for example, could where we've talked about PCA or the T-SNE, which is the T-distributed stochastic neighbor embedding, right? This is to reduce the dimensionality of data. In PCA, like for example, with like highly correlated values, it's like you can find commonalities and kind of like choose the most significant ones, right? It's like cluster the data as a feature. So this allows you, in a sense, to extract the most significant out of a set of correlated values. That's what PCA really does. So Christopher, like for example, instead of it trying to identify like a car, you might have it try to find the characteristics of a car, right? Remember, everything is pretty much converted to numbers, right? Yeah, so even the image file format, just so we're clear, is actually converted to number, like it's converted into, there's analyses, right? Yeah. So just to be clear. That does actually. We're not going into all that. Yeah. So anyway, so these are just ways, by the way, where you can extract the most significant features or condense features into the most like significant values. So yeah, we are kind of glazing over it to a certain degree, because these are like deeper topics. NLP in particular is a much deeper topic. Yes, Chris, absolutely. But there's a lot more to that. Yeah, there's a lot of how it like conducts basically image extraction of the pixel data. It also depends on the algorithm being used, right? That's a good question, by the way. So let me throw this out there. When would you, by the way, when have people used PCA versus t-SNE, right? Just out of curiosity. I'm gonna wake you up, wake you up all up a little bit. I'm glad I'm getting questions. This is good. Never used t-SNE. Yeah, PCA is probably like far more common, right? Um, we'll talk a little bit more about like t-SNE later on. Yeah, and I'll be honest, I don't know that I've used it in probably like years, right? I don't think I've used t-SNE in quite some time. I would say PCA is probably like far more common kind of embedded approach. Basically, t-SNE does like more kind of like neighbor analysis in order. Wait, say again. Yeah. So t-SNE is basically used to like reduce it based on like the like context of other neighbors. That's like the last time like it was explained to me like this is what it's used for, but I haven't actually used t-SNE in production in years, right? And even then, I think it probably been years prior. PCA is by far more common in order to reduce dimensionality. So I don't really know that I can really answer that very well because I haven't used t-SNE enough to know. Chris, no, it's used to reduce the dimensionality of data, right? Yeah, and basically it does it by its clustering the data as a feature, right? Very similar. PCA will basically kind of identify correlations between like significance in like highly correlated values, so you can kind of like cluster them together, right? t-SNE does the same thing, but it's more of an unsupervised approach to cluster the data as a feature, right? Yeah, good. It looks a little bit more awake now. Excellent. Other things to note is that in addition to feature extraction, we talked about this. We've referred to this a lot. I mean, you've got sales data, revenue data, and you've got like net change in sales, right? So, or net profit maybe, but I'm not really sure exactly what because if that's net profit, then why is sales so low? Regardless, so one thing that will happen here is that revenue might be mostly redundant, right? Because with sales here, if sales is going up, isn't revenue going up? Because that's like total sales, it's not net gross analysis, right? So revenues is going to shift in parallel to sales. So is that going to provide a lot more insight to the model, or is that a highly correlated value, right? Do we even need that number? Is there any reason to aggregate it to its most significant value, or can we just like let that go altogether? Because some of these features are going to be more important to, like, for example, we're looking for sales accuracy, like sales predictions. So revenue might be redundant in this case, right? It might not. We need to be careful with this, right? So it might not. And, net might also not be relevant, right? Net profits from sales, as an example, may not be relevant at all in this. So we could remove that feature. So feature selection just says, hey, is this the right data that we need for the model and the business problem that we're trying to solve? So, yeah. All right. So one thing you may consider is that when you have too many features in your data, you might consider using filter to filter them. Filtering the data is a common technique for filter selection. So it's basically, they're not only used for structured data sets, but like if you're doing images or audio, right? The data structure is more complicated, and you might like filter out a lot of data or a lot of images or a lot of video, right? And I think a lot of this, from my perspective, tends to occur during pre-processing, but you might find during model training that you now need to go back and take a second look and make sure, now that you've got some idea about how the inputs are going to translate into the outputs, do we have all relevant data? It's like yesterday, like when we were running through the flight delay project, there's a column that said that literally gets checked in there from the data that says, hey, what if we already had something in there that was a great label that said, if this box is checked and this flight's going to be 15 minutes plus or minus 15 minutes off, right? Usually late is what we care about. We usually don't care about early, right? And it's like, you might need to reduce the amount of data that you have, but you also need to find the most significant data. And like, for example, there was the feature already in there that actually works perfectly as a label. Then we're just going to use that, right, as our target. So this is really nothing more than just reducing the number of variables and features in order to get it down to the minimum set to make it meaningful for your model, right? Bottom line. Hope that answers your question, Chris. Right, because we're still actually about like talking about the curse of dimensionality, right? You're going to remove some features. By the way, when we say features, we are talking about columns, Chris. When you remove, right, rows of data, we're talking about removing features of the data, which is mainly columns. As an example, in this set, right, we're doing clothing sales. It's got 10 years of sales data. If you're doing swimsuits, for example, which is what the statement is here, do we actually need winter and fall? I mean, maybe you're running a sale in the fall, and that's when you actually sell a lot of swimsuits because you got people thinking ahead. But just to be frank, most people don't think ahead like that, right? Or you might find, sorry, just to say this, I have a little issue with this example. You might find, by the way, that there's a tremendous amount of sales among a certain demographic because you get a bunch of snowbirds who go down to Florida. I'm not saying that Florida, by the way, is nice and balmy in the wintertime, but maybe they don't go to Florida, maybe they go to Costa Rica, right? But this makes a lot of sense, right? Is that you got to think about like the customer and the business problem you're trying to solve. The majority of purchases for swimsuits are actually going to be in the spring and summer. Now, feature creation and transformation, unlike extraction and selection, is not a dimensionality reduction technique, right? By the way, right? This is where instead it's like you're going to generate new features from existing features, right? So, for example, date has an example is a feature, and here we're going to format it into month, day, year. Another one is, in a sense, the creation of like days of the week, right? From the actual day of the sale. Another one that you might do is that you might not, like in this particular case, you might have it where it says, January, February, March, April, May, and instead you might convert that over to the month number that you have here, or you might even do some encoding and convert it into columns, like feature columns, right? Just, be aware, right, is that adding more features to your data is going to add more dimensionality, right? And sometimes when you add more dimensionality, it's going to be hard for the model to derive a pattern in your data. So just stay aware of that. Now, depending on whether you're dealing with numerical or categorical data, the techniques you use for feature creation and transformation may be different. So let's look at numerical first. So for numerical features, some of the techniques that you could use include like taking the log, the square root, or the cube feature of the root. It also might entail you kind of bending it out where you like count the number, like existence of these values within a certain range, and also scaling, right? So scaling it, within like 0 and 1, or doing some kind of absolute mean. There's a couple methods here that we can look at. So here, like if you take the log of a feature, which is a common transformation method, it can change the distribution of a variable on the distribution plot. It can like reduce, for example, like what they call right skewness, right? To be clear though, you can't really do that for 0 negative values. Now, yeah, the natural log. Now, if you've got high variance in numerical data, such as the square root or the cube root, right, for example, this has an effect. It has an effect on feature distribution, but it's not as significant as log transformation. Cube root has its own advantages, right? It can be included to negative values, including 0. Square root can only be applied to positive values or 0. So moderate impact on the distribution of like the spread, if you will, of a particular feature. Cube root's going to have a really big impact. Other things you can do other than log, square, cube, right, is that you can bin it. So you can basically say, hey, within this certain range, I want to make this like into basically a feature column and say whether it's true. This is a great way to take a large distribution of ages, for example, and then basically like create columns for it. It basically puts data into groups. That's what binning does, is it puts data into groups. That's the simplest way to say it. So you can convert what was probably known as a continuous variable. Age, of course, has a finite range, at least based in 2022 it does, right? But it has a smoothing effect on the input data and can reduce the chances of overfitting in like with small data sets. So if you're looking at age, you can convert it into this column like child, adult, senior citizen. You could do the same thing with like states, but instead you could say, is it in the southeast, northeast, northwest, southwest? Like you could actually do it that way. Let's see, kind of a big question. Are there any rules of thumb about when to cast problems as time series? I think it depends on the business problem, Keith. Like as a time series data that needs to be solved, as a time series issue that needs to be solved. Not really sure what you're asking there. Clarify if you want to. As for transformations, I've heard Netflix engineers literally just throw random transformations and see if the model learns interesting things from them. Does this only work if there are tons of data points or some other criteria? Let's see, Chris, you're asking me if you throw in random transformations and see what the model does with the outputs as a method of experimentation. No. You're asking like, does this only work if there's tons of other data points or other criteria? No, actually, and this is that curiosity thing I was talking about before, to be clear. Again, if your like business can support this and your culture will support this, which I would definitely like make sure you're working for a company that supports this. Because I got to tell you, when you work for a company that supports innovation and experimentation up to a certain extent, right? You got to be careful. There's a trade analysis, a cost benefit there. Is that I would say like playing with the data can yield unexpected results. I've had engineers come to me and I said, like, you did what? And it's like, and then it's like, yeah. And then we found this whole new kind of dimension or effect or weight, or we found hidden bias, like all this stuff that you can do if you can experiment with the data. So does it only work if there are a ton of data points? Not at all, right? I would say that they're like being able to run a model, and let's say you get to the business objective pretty quickly, and then the model's in production and you want to discover like new ways or new experiments to do things, I think that's awesome. You don't always have time for that. But again, it depends on the culture of where you're working. I don't know that there's any particular criteria for the data though to do that level of experimentation, to throw random transformations in there. So with binning, you need to implement dummy variables or one hot encoding. I mean, you can bin the data yourself, but yeah, some of those encoders will do some of that for you automatically, right? Especially with categorical data, right? Like for example, if you got a categorical data with a number of categories, that will convert that into columns and will say, hey, is this an apartment? Is this a condo? Is this a townhouse? Is this a house? Is that kind of thing. So we'll talk about one hot encoding. Yeah. Well, of course, right? But I will tell you, by the way, it's useful to do things that you, especially if you're just messing around, it's useful to transform things that you like just are not sure, right? Obviously, everything you do needs to be geared towards solving the domain, like improving the data quality for the model. But it's interesting, like you might just not get a wild hair and like transform something and just see how it performs. Most of the time it performs way worse than you think it does, but it is useful to experiment with the data. Is there an advantage to binning as opposed to augmenting the amount of data overall? When you say augmenting the amount of data, you mean adding more like of the total data to it? Because I think what you're doing with binning is that you're kind of like adding more richness to the dimensionality of the data, right? You're extracting, in a sense, kind of more features to the data you have, right? And it basically, when you do that, right, it's going to remove kind of like large deviations or outliers in the data, right? It's going to simplify the analysis because you're basically, even though you're adding dimensionality, you're adding really simple and meaningful dimensionality sets to the data. Because you might not care what someone's age is, but you might care whether they're a kid, an adult, or a senior citizen. So again, it depends on your goal. So like if our outcome here is that, you know, I am trying to identify people who are over the age of 60 and exclude people, you know, underneath, or I'm trying to determine, you know, the probability of buying based on a certain kind of like a stage of life, then this would probably be more useful. Yeah. In the examples that I gave, right? Yeah. Here's here's, by the way, an example of like scaling data, right? To avoid having like one feature have a lot more importance than others due to the original range. So this is kind of an important technique. Like for example, here bedroom has a value of 1, 2, and 3, and then here you've got a range of pricing, right? So there are not many bedrooms in the house, but on the other hand, the price of the house ranges from 300,000 to 1.25 million. That's a huge difference, right? That's a huge difference in scale and can give disproportionate influence to largely scaled variables. Because remember, something that has a large like data range, a large distribution is probably going to have like a lot more effect on the data, and that might not be what you want, right? Again, it just depends on the business problem that you're looking for. So Devin, when would you want hot encode those bins versus leave them as a single column? I think we explained that, but like it's when you like, maybe you don't care about exact age, but you want to like, you're looking for like someone in a certain stages of life. You want to basically create dimensionality that is specific for the business problem you're trying to solve, right? But you've got the raw data, which in this case is the age, but that may not be what you're looking for. And so you want to like scope it out a little bit stronger towards the business problem you're trying to solve. Now, scaling is important because we're mentioning the whole bedroom versus like the house, is that most, but not all of the machine learning algorithms are actually sensitive to different ranges of data, right? Like I said, a wide range of data is going to lead to some optimization challenges, right? But things like anomaly detection, they're not super sensitive, right, to scales in variables in the data set. So you might want to basically align all the features onto a similar or same scale. This is where there's a bunch of scaling transformation techniques here. And again, we're going to show the math, but you do not need to know the math for any of this stuff, right? Just to be clear. So these are commonly used scaling techniques that allow you to kind of like normalize ranges, especially when there's a large deviation, large distribution of the values in a particular feature set. So you can apply a transformation to a particular column, and then, you know, different columns are scaled independently, right? So the most widely used scaler, right, is the standard deviation methodology using mean and the variance, right? Now, I do want you to note something, because this kind of shocked me on my exam, is that it did ask me, it basically said, you know, we're wanting to like, you know, apply standards, standardization, standard scaling basically to our thing, but it didn't use the word standard scaling. It used something else. I don't think it was mean variance standardization. I can't remember the exact phrase, but in the answer, it basically listed standard scaler in that like exact language, which I only knew because I had seen it in the scikit, right? So scikit-learn, and I was just like, wow, they actually put like a small code reference in here, right? So just remember when you see the standard scaler, if that pops up as an answer, they're talking about the most popular scaling technique, which is the mean variance standardization, right? So when you run something through this transform, what's going to happen is that your features are going to be on the same scale with a mean of 0 and a standard deviation of 1, right? So the optimization algorithm for any machine learning methods are going to be more likely to converge because there's less of a range, right? So it will still keep the outliers, but it's going to reduce the impact of those outliers significantly. Other types of scaling, right? Min-max scaling, right? Again, you can see the min-max scaler listed there. You find the minimum value and the maximum value for a feature that you want to scale, and then you subtract the minimum value of the feature and divide it by the difference between the maximum value and the minimum value. So anyway, you can see the math there. So again, after transformation, the new variable is going to be between 0 and 1, also called from the scikit package. Oops. So the advantage of min-max over the standard scaler is that it's really great for cases with like just a small like standard deviation. So when the standard deviation is small, the mean variance scaling is not going to be robust because you're dividing by a very small number in the standard scaler. But it doesn't. This transformation doesn't really change the distribution of features, right? So because of this, outliers are typically more impactful when you do min-max scaling. Because of this, it's typically recommended that you handle the outliers before you do min-max scaling. Again, max absolute scaling, right, is in this particular case, you take the absolute value, find the maximum of that absolute value of that feature, and then once you find that, you're going to divide it by pretty much every element. You're going to divide every element of that by the absolute value for that particular feature. Max ab scaling does not necessarily like destroy sparsity because you don't center the observation, you just scale it. So you can also call that from the scikit process as well. So there's max ab scaler, there's the min max scaler, and then this is the standard scaler. Probably good to just know that in general, they're pretty intuitively named. There's the max ab scaler, there's the min max scaler, and there's a standard scaler. Just since that did pop up on my exam, I'm assuming there's other questions where they refer to programmatically to the scalars, right? Divides all the data in a feature by the maximum absolute value found in that feature. Yeah, it's a good visual. So Chris, if you have, for example, a wide distribution data, or you have an algorithm that's very sensitive to wide distributions in a feature set, that's when you would basically scale them down. Like this is the whole conversation around normalization and standardization, right? Would you use them on all columns? It depends on what the like distribution of the data is of the feature. And then the last type of the, if I remember correctly, is this is robust scaling, right? So you look at a particular feature in the data set and you find the median, the 75th quartile, the 25th quartile for that particular feature in the training data. Once you figure out those three qualities, right? Which, you know, by the way, you can see Q50, Q75, Q25 there, right? Once you figure out those qualities, you basically calculate the robust scale by subtracting the median of the feature and then dividing it by the difference between the 75th quartile and 25th quartile, quantile of that feature. Not quartile, quantile. All right. So after the transformation, it will be robust outliers because the outliers are going to have a minimal impact when calculating the median and the quartiles, right? But robust scaling can be done using that robust scale function like you see there, the robust scaler inside the scikit. Let's see, there was a great link in here. Hold on, I remember seeing it somewhere. There it is. Let's go take a look at that. Oh yeah. There's some plots of all the scaling. So something to kind of add to your like training toolkit to see exactly if you're really interested in the behind the scenes math about how these scaling algorithms actually function, or transforms actually function. Okay, so let's shift some of the transformation techniques over to categorical data and not numerical data, right? So when you're dealing with categorical data, right? So in this case, like ordinal versus nominal, right? You'll often need to convert the data into numerical data before it can be read by your algorithm, right? Now the approach is going to be different depending on whether or not it's actually, ordinal or whether it's just a name, right? They're not ordered, they're just nominal. Now, if you look at the housing data that we were just looking at, the data set includes these several features. So type, bedroom, area, garden size, price. There's also a yes, no value, which is the target variable indicating whether a home loan was approved or not. Now, house type over here and garden size, in a sense, represent categorical features. Garden size, more specifically, you could say it represents ordinal data because small, medium, large can be represented in an order, right? In could be no garden, as an example. So then what happens is you can just convert the text into a numerical value, right? Because notice that back here it was small, large, medium, not applicable. And what we can do is we could actually convert that into a numerical value. You can do this in pandas, by the way. And so you could define the relative difference for those categories and just define them into like whatever numerical value makes sense. And so then it just becomes a one-to-one mapping. 0 means you don't have it, 5 is a small, 10 is a medium, 20 is a large, right? By contrast, it's not generally recommended to encode nominal variables, for example, to basically numerical data, because then the increasing value of the number isn't necessarily going to denote some kind of increasing value, like large, like t-shirt sizes, for example, right? Because when you do that, it implies they have a numerical value, they have an order difference, there's a magnitude between the different numbers, and these additional features are not really something that belongs to the original data. This could give you wrong or unexpected results, but you still want to convert these categories into something like these are just names. They're not ordinal, right? They're just names. You still want to convert them into something that's meaningful for the algorithm. So this is where one hot encoding comes in. It's where you want to take this nominal, categorization, and you want to convert it, right? I mean, I don't know that at Decode, honestly, I would do such a large spread. I probably would actually do 1, 2, 3, but I mean, honestly, a 0 to 20 range isn't going to be huge as far as like distribution goes, especially with the steps involved, right? Because I mean, 1, 2, 3, and 4 would be the same thing as like no, small, medium, large, right? Sometimes people do that to denote that like if the square footage doubles in size. So for example, 0 obviously is nothing. Maybe it's a 1 if it's small. Obviously it's 2 if it's double, it's a medium. Maybe it's a 4 if it's a large, 8 if it's an extra large. I probably would be more likely to do that, right? Instead of just keeping it 1, 2, 3, just because I would still want to note a relationship about the size of the garden, but it depends on the specificity. Maybe it doesn't really matter. Is there in a garden? Is it of a certain quality? Right? It just depends. But 1, 2, 3, 4 could work just fine. So here we've taken like the type house, type apartment, and we've converted in basically into it's almost like a Boolean, but it's really just a binary definition, right? 0 and 1, right? So you just convert it into 0 and 1 with one hot encoding, right? The get dummies function in Panda, by the way, will actually create new columns based on one hot encoding, and it'll create the column names for you based on the prior nominal categorical names, right? So in this case, you've replaced it with home type. Now, oh yeah, I mentioned this earlier. So yeah, so just to say this, it's like, well, what if all of a sudden you decide you're going to do this and you add 100 columns, you had 100 features to your data set, or you've added 50. Do you need that? Like, don't get me wrong, you might want that might be meaningful data, right? As far as the US states. It might not, actually, depending on your business problem. So you might actually want to go against like kind of cardinal like regions, if you will. You could also, by the way, do it based on quality of landscape if you're looking for something like that. Again, it just really depends on the business problem you're trying to solve, right? On whether you would do one hot encoding, whether you would minimize the deviation, like because you're looking to minimize outliers, whether you would do normalization, standardization, scaling. It really just depends on what you're trying to solve and whether that's going to like impact your data or not. So just to say this, a lot of you are asking questions like, well, when would we use this versus using this versus using this? And I can't give you a blank answer because it's really going to depend on the business problem you're trying to solve and the data that you have. So I wish there was a one size answer, but I don't have it. This is the part where, I was having this conversation the other day, where you're really, you just like, this is one of those roles where you really actually need to just be doing it. You need to just do it and try to peel it back, understand it, and apply it, because the context constantly changes, right? It's a little different than if you're like working, if you want to stand up a virtual machine or a container, or if you want to write a module function. Not that doesn't run into it with software engineering as well, but the ways to get there really are really contextually dependent. So if you really want to master this, you're just going to have to practice it. Chris, that's a good point, right? Yeah, or tourism, any kind of tourism thing, vacations, that kind of thing. I'd probably throw a mountain in there, right? People love mountains. Is there a valley? That kind of thing. But yeah, sales of fish, right? That would be interesting. Island, coastal versus inland. Yeah. So instead of just breaking them out into one hot coding, you might group them by similarity, right? And you might create new groupings. This, by the way, will give you the benefit of meaningful interpretation of what state could mean, while not vastly expanding the dimensionality of your data by adding a whole bunch of new columns to the data set. Okay. Let's talk about hyperparameter tuning. This is another rabbit hole that we could go down, and we're gonna move through this. Just be aware that your lab that you're about to do, lab 4, which is going to be the final lab, is going to cover a lot of these pieces. So you're going to see it in action. Oh, that reminds me. Just make sure I do this really quick. I just want to make sure everyone's taken care of when it comes to this. Let's see, what did I do with this thing? Here we go. All right, I'm going to pre-warm your labs just to make sure everything's good. All right, 8 hours. Perfect. Okay, cool. Okay, so if we go back a little bit and away from feature engineering and into hyperparameter tuning, this is how we improve the model, but we're not touching really the data. We're not touching the data. So instead of touching the gas that's going into the engine, we're actually tuning the engine itself, right? There's a couple of different aspects to this. There's the model, right? So there's a couple of different kinds of hyperparameter categories. There's the model, there's the optimizer, right? How the kind of model learns, if you will, right? And then you could actually define attributes of the data itself, right? So again, we could touch the fuel, we could touch how the engine works, right? We can touch how the engine learns. Now, hyperparameters, just to make sure I'm clear about this, can be thought of as the knobs, the dials you can turn, the values that you can change that will improve its performance, okay? So filter size, pooling, padding, those kind of things, gradient descent, stochastic gradient descent, and then, we've done through some feature engineering already. So, but there are some hyperparameters that relate specifically to how that data is managed and attributed, right? This could be everything from cropping and resizing for image related problems to, certain stop words inside of text, problem challenges, right? So there's a couple of methods. One is that tuning hyperparameters manually can be very labor intensive, right? Someone who has domain experience comes in and tunes that related hyperparameter, and they would manually select hyperparameters based on their intuition and experience. They would train the model and score it, right? You'd repeat this process over and over again, turning the dials. And if hyperparameters have like a wide range of values, is there just some way that you could just test all the permutations of all the hyperparameters? Is there some iterative way you could do that? Now, grid search is one of those methods where you're going to train and score for each possible set of hyperparameters, right? What's the problem though with taking a model and then running it through every single possible hyperparameter? What's the challenge with this? Yeah. Dakota, sanity. Possibly, but like if you're doing it manually, yes, that would probably cost your sanity, right? But definitely in terms of time, which I'd argue probably is a little bit more valuable than money, but money is still super valuable, right? Sanity, we all lost that a long time ago when we said yes, not just to this class, but just to getting into the IT industry. So maybe. So the problem here with grid search is that you're going through every single combination of a given value, right? So this is going to be thorough, but this can be super inefficient. Random search is similar to grid search, but instead of training and scoring on each possible hyperparameter combination, you're just going to select a broad swath of random parameters, of which you can set the number of search iterations based on time and resource constraints. So it's not like it's going to do it infinitely until it exhausts every single possibility of randomness. Sorry, I lost my train of thought there for a second. So I think I've said this before, but grid search isn't really supported, and that might have changed since I even just said those words. But in general, they have not supported grid search inside of the hyperparameters. They support random search. And I remember I was asked at least one question on that on the exam, right? Where they were trying to catch me and like, hey, we're going to use grid search. Or there was one about Bayesian optimization. See there, I just pronounced it differently than I did before. Bayesian operation, where, Bayesian is more sequential. So like you can't run that concurrently. Whereas random search could actually be run concurrently. So here's a Bayesian search, right? So instead of doing random, by the way, or running through every possible parameter, Bayesian search basically treats like a regression problem, right? Given a set of inputs, like the hyperparameters, it's going to optimize the model for the metric you choose. It's going to make guesses about which hyperparameter combinations are about to give the best results. It's going to run training jobs to test the values. So it's going to learn from each set of hyperparameters that it's running. And so it's just going to experiment, right? But it is going to try and shift values to optimize. So it might choose values that are resulted in the best, that are like close to a previous training job, to see if it can incrementally like improve in performance, right? To kind of like get the best predictive score, reduce the minima, all that. SageMaker doesn't do grid, right? Yeah. So random and Bayesian are the two best options. One just a statement about Bayesian, make sure this is super clear. This is an incremental learner, right? Because it's a sequential learner. You're not going to be able to parallel, like adding more, like running more jobs in parallel, or adding more like nodes to the equation in this, especially if you're not doing distributed. That's not going to help. You want to, this is going to train, take the result, and then improve upon the result, train, take the result, improve upon the result, train. It's going to keep doing this, but it's very sequential on how it does it, right? Whereas, you could actually do random. You could run a couple of like different jobs, training jobs in parallel, right? And just see what the outputs are. And as long as it's tracking the hyperparameters that it's randomizing, it's not an issue. I just want to be clear that this one's not going to scale from a parallel perspective. Doesn't make it something that you don't want to do. But on the exam, if they like imply that somehow this is going to scale, it's not going to scale. Like it's not going to distribute. It's not going to parallelize. Doesn't mean you can't throw more horsepower at it if you want it to go faster. Yeah. Now, SageMaker offers automated hyperparameter tuning, right? And it's going to use things like Bayesian optimization, gradient descent, and different kind of algorithms to conduct a guided search for the best parameters. So this will let you do hyperparameter tuning, right? To find the best version of the model, and it's going to be running many data training jobs on your data sets using the algorithm you specify and the ranges of hyperparameters that you say you want, right? And so it's going to just keep going. So it uses a Gaussian process regression to predict which hyperparameter values might be most effective at improving fit. It's also going to use Bayesian optimization to balance exploring the hyperparameters and exploiting specific hyperparameters. So this can be used, by the way, with any of the built-in algorithms and frameworks with like no notable exceptions. It also can be used, by the way, with the bring your own algorithms as well. So pretty much anything that you want to do on SageMaker, you can run a hyperparameter tuning, automated hyperparameter tuning. No, excuse me. That tuning is not always going to improve your model, right? So it's just part of the methodical kind of scientific method you're going to follow. So, and exploring all of the best practices, no. So, you don't want to adjust every hyperparameter. So limit the number of hyperparameters to ones you think will most likely give you the good results. So explore what the hyperparameters do. Like look at the documentation and find out what hyperparameters are relevant for your particular model and see which ones you think would be the most impactful based on the data set and the problem you're trying to solve. The range of values that you choose to search, especially when you're doing automated tuning, hyperparameter tuning, can significantly affect the success, right? So consider doing a limited range or like scopes of ranges at first. So just know that SageMaker, by the way, will actually try and figure out whether your hyperparameters are log scaled or linear scaled. It's going to assume in general that hyperparameters are linear scaled. So, if you know that a hyperparameter is log scaled and you can convert it yourself, you might want to just go ahead and convert it when you input it in the SageMaker. Run one training job at a time rather than parallel. Yeah. If you're doing Bayesian, sure. If you're doing random, there's actually nothing wrong with that because you're just going to like calculate the result. Yeah. All right. So, we're going to be actually doing hyperparameter job, and just for the sake of time, I'm not going to peel that back, right? But I do actually have a short video showing me running through hyperparameter optimization. I'll actually throw that into the video list as well. But just for the sake of time, since I want to make sure that we have plenty of time for the lab, I'm going to forego that for the time being. Okay, so our goal here was to basically explain the possibilities of feature engineering, which basically falls into feature extraction, right? It can be scaling, you could be encoding data in order to convert it from like categorical data, nominal categorical data into something that's a little bit more numerical, right? Because you're going to need that for your algorithm. We talked about things like logarithmic transformation, whether it's square or cube, or putting things in groups with binning, or doing like a sort of standardization using like the standard scaler min max, right? Max abs, robust. And then we talked about just briefly the 3 categories of hyperparameters, just model hyperparameters, optimizer, defining how the model learns patterns, and then different kind of like data hyperparameters like cropping and resizing. We just mentioned that in passing. Okay. So a couple of just reminders around the best practices, right? Make sure that you're limiting the number of ranges. You convert log into linear. If you're doing a distributed training job, make sure that your output objective is the one that you're actually looking for. Like make sure that's clearly declared. Remember that running more than one job can be useful, but it also depends on the kind of optimization that you're looking for. So remember that Bayesian does not distribute or parallelize very well. And as far as the techniques go, you can't use grid, but you can use random search or Bayesian optimizations when you're doing the parameter tuning. Okay. Yes. But in other words, it could eventually figure out that you submitted that it's log scale, but if you know that, then just go ahead and convert it into linear and submit it, right? Don't force it to figure it out. You're going to be wasting time while it basically discovers, right, that it's log scale. Okay, so let's talk about lab 4 with feature engineering. So this one, again, little distinctions here. We're definitely not going to break, right, for this. You're going to, just like yesterday, you're going to upload your lab 3 file, run through everything until you get to lab 4. Note new bucket. Okay, good. And then you're going to complete the actual like hyperparameter optimization file. And then from there, what's going to happen is that you're going to complete the actual lab, and then you're going to apply what you learned from the lab to complete your thing, and then you're going to download your file again. Are you going to download your file again? Just to keep it for yourself. You know, I'll be clear, sourcing the data, sourcing that training data, if it's the open data, is probably easy to do. If it's pulling from one of the TC buckets, you know, that, you know, you're gonna have to like source it from the open data itself, because those TC buckets are locked down and private. That whole Quick Labs environment is pretty locked down. I'd probably use one of the SageMaker workshops or the book that I shared yesterday if you're looking for further kind of explorations on SageMaker. Okay. Pulling down these labs and kind of recreating them, given the lockdown nature of Quick Labs and the lockdown nature of the Amazon buckets, has been super problematic in the past. Okay. Now, I wanted to maximize the amount of time that you had to do this. Do note that this is the last day, right? So unfortunately, I don't have as much fudge or wiggle room around how much time we use to approach this, but we do have 2 hours and about 15 minutes or so. So that's what you're going to be doing for the next 2 hours. Before we move forward, does anyone have any questions about anything that we talked about? Any questions that weren't answered? Oh, Matthew, thank you for calling that out. Sorry. Funny, I saw Joel's statement. I didn't see yours. Pre-assessment question 1, grid, random, and Bayesian, which, yeah, exactly. So random, obviously, I'm sorry, grid would be the answer now. Okay. Are we able to work on the other 2 labs after the class ends for practice? Yes. So just remember that you have access to run these labs a total of 3 times each. So you can definitely go back. You have access to them for 90 days. So, right, that you can actually use. one of the things to mention is that, uh, so sorry, one example of hyperparameterization on data itself, for example, kind of like, in a sense, I would probably look at more like cropping and resizing, where you're like tuning the things, whether when it ingests images, it modifies them in some form or fashion, right? That's also something, by the way, you can do in pre-processing as well, using data augmentation techniques, right? Introduce variability in images and how they're like, how the model, for example, might manipulate text or images. So we did cover this, but it's okay, Chris. You can ask, is that grid is just inefficient, so they don't like to use it, right? Because if you're running through all of the possible hyperparameters, they've just found that, one, it doesn't yield optimal results in a time frame that's worth doing. Yeah. Yeah, Jonathan, I can't answer that question as far as why there isn't a big hypernob labeled accuracy. Let's see, is auto hyperparameter tuning, I'm assuming tuning, right? An expensive service? I can't really answer that, Dakota. It depends on your data set, what you're doing. Like, as far as like, how much does it cost, or is it valuable? I mean, I think it's valuable. I think in terms of like, is it expensive? I think it depends on the range that you set, the number of iterative, like for example, if you're doing random, the number of iterative searches that you want it to run through, the number of iterations you want it to go through, the range on the parameters themselves, how effective your model is already versus like how much optimization do you need to do? Yeah. If you run it just inside the console, it's for the life cycle of the instance that you start. So if the training time is, 300 seconds and the instance starts, it does the training and then it yields the result and then shuts down, then you only pay for the training time. So you only pay for the time that it's actually running. Yeah. Yeah. Unlike notebooks or Studio, with the pricing for SageMaker is that if you start up something to host a notebook or Studio, you pay for the life of that virtual machine for as long as you've got it up and running. If you call and code another like training job or a hyperparameter auto tuning job, and you call that and it takes 500 seconds to run, you're only going to pay for 500 seconds. So it's funny, like inside a notebook, when you run code and you call other systems and you specify the size of the virtual machine, that machine's going to spin up, run the job, and then it's going to drop, right? It's going to shut itself off. So you should only be paying for the training time at that point in time. Someone was asking like the schedule for this afternoon. So what we're going to do now is it's going to be 2 hours and 15 minutes of you running lab 4. And then after lunch, we're going to do just a little exam prep. It's going to be it's kind of the final step, just a reminder of everything. And then we're going to run through some exam questions. And then we're going to talk about deployment. We don't have a lab for this. We're just going to talk about deployment. Deployment tends to be more on the ML ops side kind of things. And then what's going to happen is that we're going to like close it out after we talk about deployment. You're going to do your post evaluation, your post assessment, just so you can see like where you landed. And then that's going to be the end of our day. Okay. So Keith, you're working on your project now. You're actually going to go through, right? You're going to, number 4 says apply what you've learned from the hyperparameter optimization project to complete the feature engineering section for your project. So yeah, that's what we're doing now. Okay. Hopefully some of you are ignoring me. Hopefully those of you who had questions got those questions answered. Yeah, so we're on the lab 4. Okay. Thanks everyone. All right, I'll be here. I might step away for just 2 seconds, but we're all working on lab 4.